Okay, welcome back, everyone. Yeah, so we start again with the Q&A session regarding the talks of the previous day, but also kind of regarding maybe any open questions that you want to discuss. Also taking into account people from New Zealand, for example, who are not going to be there in the evening discussion session. I'd also like to point out that on Mattermost, there's been quite some activity since yesterday, people proposing projects, concrete projects that could actually kind of be implemented or take off as a follow-up of this workshop. So that I think that's definitely something we should follow up on, and I encourage people to propose projects or to think about if they would like to participate in projects, or also think about kind of if they have an idea in mind, kind of what type of expertise will be required to complete that project. Maybe that expertise is somewhere in this group, because we do have kind of quite a diverse bunch of people here.
Just to say that I'm trying to collect these projects, like with title and a brief description, in a Google Doc that was created by Sebastian Klesse. I will circulate it later so that people who are interested can like add their name, and we can follow up with that. Yeah.
Sounds good. Okay, so I guess the floor is open. If there are any questions regarding yesterday or regarding any other part of the workshop, quite a few of yesterday's speakers are here. So feel free to either raise your hand or just speak up. Okay, so then I'd like to maybe to start. So I saw a discussion between Nancy and Juan on Mattermost, and since Juan is here, I'd be curious to understand maybe what is the question and kind of what is the status a bit better.
So Valerie, there were several discussions we had. So which one do you need?
It's okay.
I'm sorry. I've been
right.
having a lot of discussion with Nancy.
Right. So I'm referring to the question of the memory effect, right? And
okay. Okay.
If we can if there have been put bounds already, and if
I read the paper of Eric and others. They missed something which is very basic in interferometry.
Maybe you can just recap.
Okay. So the idea is that when you have a gravitational wave that goes through a detector, it leaves. Well, it depends on what size of event that is. No, but it leaves an offset with respect to the amplitude of the incoming wave. So typically you would argue it oscillates around a vacuum. You've already defined your space-time. So you have a fluctuation, this is your wave, which distorts the space-time. And it has a certain amplitude with respect to the mean. And then finally there's a chirp and a merge. And when it merges, the oscillations, so they ring down all the way back to flat space-time. The ring down happens at a different level than where it started from. And that's called the memory effect, okay? Now, this is something which, indeed, if you have an accumulation of such, if you could remain with your basic, so your base, no, amplitude, your space-time, and you had a series of waves that come through, it would successively increase, and you could have a significant displacement with respect to the base. Now, what happens, and this is what was missed in that paper, and I mentioned this in voice before Nancy's comment in the Mattermost, is that the interferometers do relocking every X hours. I don't remember how much, and that depends on the day. No, there are sometimes, if you go to the activity of LVK, well, ligand Virgo mostly in run 3, if over a day, you will see that sometimes they just simply stop and then they come back again and so on. So sometime, X varies from between a few hours to a day. They have to relock again. Okay, that means that they have to do the interferometry when it reaches the photodiode to see that they receive the photons from the lasers. That is put at 0. So that means that you're redefining your base space-time again every time. So you cannot keep on adding the effect like Eric was assuming. All right. So when you have, unless this is the key point, unless you have simultaneously at very high frequency an event, simultaneous with an event at low frequency, so that they would be capturing right at the same instant at which the large event is detected at 100 hertz, they would be capturing also the kilo, gamma, mega or gigahertz event. No? Then there could be a chance to see that there is this extra offset. Otherwise, it's very difficult.
So is the offset kind of, okay, I see your point if kind of the offset is really exactly constant, or rather if kind of if I do a Fourier decomposition of the offset, right, if that is a time which is much longer than the locking time?
Yeah, right, the offset is the pseudo mode.
So it's exactly the 0 mode, okay.
Yeah,
because otherwise,
sure.
If it's just some very long wavelength mode compared to, okay.
So essentially it's telling you what are you fluctuating with respect to what. So if you say this is my background, and then you do the fluctuation, this is your gravitational wave. Remember, gravitational waves are propagating in any backgrounds, right? So typically in like at CERN or like in LIGO, you take a background which is just flat space-time. Obviously, there are fluctuations due to the Earth, which is putting Newtonian motions and many other things, right? So you have to keep those fluctuations to the lowest level possible. And then when you reset your experiment, that's called relocking, you just set it to 0. You just tune so that your laser, by changing the arm length, so the laser exactly in the photodiode, there is no signal. That's what's called locking. It's a destructive interference. So if you happen to have a displacement, you would keep on having some non-zero destructive interference, so you have some constructive.
Okay, thank you. Any other questions that people may have, or thoughts or comments?
I wanted to ask Richard to expand a bit on this matter domination, early matter domination. If you can tell us a bit which kind of scenarios you have in mind and what's the state of the art.
You're muted.
Yeah.
This is something that's talked about a fair bit over the years, and in some ways, you know, I mean, this is going back, you know, like through to the first slow roll models that were proposed, is that there wasn't a clear idea about how to bring them to an end. And so, you know, I've always felt that like people develop these inflationary models, and some of them are better and some of them are, you know, kind of pulled out of thin air. But the thing that's kind of speculative squared in some sense is that none of the, or very, I mean, I think Juan mentioned the possibility of Higgs inflation the other day, which is an exception. But many of these scenarios, you know, people write down a potential in some very high energy theory, and then they don't necessarily have a clear sense of how you're going to couple the quantity that, you know, that eventually you produce in those fields to the standard model, you know, bring about a thermalized universe. And so lots of these models actually, I mean, in some ways, I think up until the mid-90s, you would have said that the default universe was one that had a long matter-dominated phase just because the reheating went through perturbative channels. And that took a long time. So typically people expected that the universe would reheat at like 10 to the 7, 10 to the 6 GeV, something like that. But it had been, you know, inflation was, you know, orders of magnitude higher than that. So from that point of view, there's nothing special about a long matter-dominated phase. The question really is what can happen inside of it. And I think, you know, I mean, again, one of the things that sort of surprises me about this is that actually, who was I talking to? It was a conversation that I had. Actually, I've gone blank on the name. But I was talking to one of the participants here who'd looked at the possibility of black hole formation in the post-inflationary universe. And so there's lots of there's lots of things that can happen just because this matter-dominated phase lasts long enough, maybe for the universe to grow by a factor of 10 to the 12 or 10 to the 13. And if you compare that to the matter-dominated phase in our universe, where we've seen a growth of maybe 10 to the 5 before the dark energy kicks in, then there's the possibility of having quite complex nonlinear physics. And it's relative to the local timescale, it's actually gone on for much longer than the matter-dominated phase does in our universe. It produces galaxies and clusters of galaxies. So in that sense, I think it's actually pretty open. I mean, the other possibility is that you have not long after the end of inflation, you have this phase of parametric resonance, and that that's very clearly associated with the production of high frequency gravitational waves, and I think fairly generically. But then the thing is that after resonance is over, there's no immediate guarantee that the post-resonance universe is thermalized. So you can very easily have resonance involving states that are relatively massive. And so, they quickly become non-relativistic as the universe expands. And then again, you're left with a bath of quantum fluid, but you've reprocessed its, power spectrum relative to what it might have been if if the resonance hadn't taken place. So it's pretty open-ended, and I think that means that there's lots of opportunities to produce, strongly nonlinear dynamics in the matter part, in T mu nu, if you want to think about it like that. And whenever that happens, there's at least the possibility that you're going to produce some gravitational waves, and you have a very generic argument that those, the scales at which nonlinearity is taking place are going to have to fit inside of the Hubble horizon, post-inflation, and that's going to be even when you scale it to the present, to present day co-moving sizes, that's going to be a relatively high frequency proposition. In some cases, very high frequency, things like primordial black holes. Those are very small relative to the horizon when they decay. And so you can very easily get, 10 to the 16, 10 to the 17, 10 to the 18 hertz out of your gravitational wave background in those scenarios.
If I may ask a follow-up question on that, because I see what you mean with the nonlinear effects, right? But also kind of a phase of during matter domination, right? Kind of all radiation energy, including gravitational waves, is redshifted stronger than the kind of
So that was one of the things that exactly. So that was one of the things I mentioned is that if you produce the gravitational waves early in the process, then they'll be diluted by the matter-dominated phase, and so the time it takes. If you have some very strongly nonlinear phase, something like a phase transition, but at very high energies, then you'll produce, very sharp, high amplitude background of gravitational waves. But then you'll lose, however many times the universe grows larger during that phase, during the subsequent matter-dominated phase, you're obviously going to dilute the relative amplitude of the gravitational wave background by exactly the same factor. So presumably the gravitational waves that you're most sensitive to would be the ones that were produced towards the end of that phase rather than at the beginning. The universe does become presumably lumpier. This is all very hand-wavy. I guess part of what surprises me is that it hasn't been worked out in as much detail as you might expect, even for the simplest models. And so this is something that my group here in Auckland, but also Jens Niemeyer and people at Göttingen that we're thinking about now, is that now we've got the computational tools to actually analyze this scenario in some detail. Then there's a greater opportunity to figure out what the background might be. But there's certainly, the way I would think about it, particularly in this context, is there's a lot of scope. Where we don't understand the physics, where we know we're not radiation dominated, because the one thing worse than being matter dominated is being radiation dominated, because that's very unlikely to produce the sort of density gradients that you need to drive gravitational wave production. So you definitely want to be in in a phase where something you just don't want a universe that's full of relativistic quanta that is simply free streaming. That's less likely to produce the kind of signal that would be interesting to from the context of the discussion that we're having here, I think. But I guess the takeaway from this is that A, we don't know, but B, there's plenty of scope for a long matter-dominated phase. And whenever there's matter domination, I think there's the possibility that something interesting is happening. But it will depend on the detailed physics and particularly the thermalization mechanism.
Richard, what is the difference between that and what we call modular domination in string models? Like you have a scalar field misaligned after the inflation and it starts oscillating, and then you get like the same equation with status as if it was matter dominated.
So I think it's the same phenomenon, and so there was there were stuff that my group at Yale, when I was there, so a student there, and Rafael Flauger, who give full credit, did the calculation, and he was a postdoc there at the time. And so all we did was to look at an n squared phi squared inflaton field, which is oscillating around its minimum. And so there's a result going back to the 80s, the early 80s, that if you average that over a single period, it looks like a matter-dominated universe. Exactly. And I think the string moduli look like a matter-dominated universe for precisely the same reason. They've got, as long as they've got no interactions, then they're just sloshing around the bottom of the quadratic potential. Okay. And so the interesting thing about that is that then you say, well, if it's a matter-dominated universe, then I would expect that the perturbations in that universe would grow as a function of time, just because it's a perturbation in a matter-dominated universe. And so what you see is that modes that have a wavelength that is bigger, or a frequency that is smaller than the sloshing frequency, which is given by the mass of or the inverse mass of the field. Is that right? The inverse mass, the frequency goes up as the so it goes up as the mass of the field, one or the other, right? Then there's a natural cutoff in the spectrum in some sense, because modes that are short enough to resolve the sloshing of the field will not grow, but the longer ones will. So as they're stretched by the expansion of the universe, the sloshing timescale is constant because it relates to some number in field theory, whereas the co-moving size of the modes obviously increases as the physical size of the modes increases as the universe expands. And so in that case, for the string theory moduli, I think you would have to figure out what you expected the primordial, the amplitude of the primordial perturbations and the density of that fluid would be from place to place. And once you're looking at, and that's not, that's presumably, even if they're not the inflaton per se, or they're heated up by reheating, or, at the very least, you've got just the fact that delta phi is proportional to h when you're on the horizon. So, you'd be able, presumably, that's a calculable, it might be more like a curvaton calculation, maybe. Then the same calculation would apply. This is what's effectively matter, as long as you're not looking at it on scales that are short enough to see that actually secretly it's the sloshing condensate. And so on long scales, you don't see that. You're effectively doing a WKB approximation, and so that short scale just falls out of the problem, and it behaves like any other pressureless source of matter in the universe. And I haven't done the calculation, but my gut is telling me that the string moduli fields would behave the same way in that context.
Right, because essentially everything you said yesterday about the parametric resonance and oscillons and so on, instead of just talking about the inflaton, you can talk about this modulus, and that's the.
It's probably not. It's, I mean, this is something, moduli and string theory is something, that I've thought about it various times in my life, but not recently. But my guess is that, obviously it depends on the mass of the moduli. So if the moduli have a very low mass, then their sloshing time is relatively long. And so then it's only the longest wavelength modes that would be in resonance. But it's very, very similar to the problem of calculating there are these fuzzy dark matter scenarios, or ultralight dark matter. I know that some people, maybe, in fact, I'm sure I've seen you, pretty sure I saw a paper from you looking at these. And so the problem of structure formation in the present day universe in ultralight dark matter is exactly the same problem, because on very large scales, we expect it to behave like regular cold dark matter and produce the large scale structure that we expect. And at some scale that relates to the Compton wavelength of the particle, we start to see that the structure gets washed out. And so that would be exactly the same problem. This is the argument that Jens and I have made, is that exactly the same analysis that you do for fuzzy dark matter in the present day universe, after, you have to tweak parameters, 10 to the minus 21 electron volts goes to 10 to the 12 GeV or something like that. But it's essentially, the math is essentially the same once you sit down and actually start to do it. Yep.
Yeah, I just see that Geraldine has a hand up.
Well, I just had a short comment, just that you can to invoke scalar field dynamics. For instance, there are these heavy dark photon models. So you can produce in the early universe a heavy dark photon through thermal effects by kinetic mixing with a visible photon, right? And then this particle is very massive and at some point dominates the energy density of the universe, produce a matter era, and then the matter era ends when this particle decays. So that's another example how you can generate a matter era in a very simple framework.
I mean, I think another way to think about it is that, the argument that is that there's like 15, 10 to the 15, 15 decades worth of expansion between the end of inflation and a kind near gut scale model and say the TeV scale where we think we might want to be thermalized by. I mean, the TeV scale is not, that's not a hard limit, but anything else you've got, if you go well below that, you've got to kind of smuggle your reheating mechanism into physics that we can experiment, that we can detect in experiments. And so that's an awful lot of growth. And I think the idea that the universe is just kind of quiescent and radiation dominated through that phase, that's quite a big assumption. And the general argument, I think, is that if you go and look for if there is anything strongly nonlinear phase during that very large and very unknown piece of the growth of the universe, which is done in a trillionth of a second, but from a scale point of view, it's half of the expansion that's happened since the end of inflation, then there's plenty of opportunities to produce gravitational waves. And as long as you're not too close to the TeV scale and sort of getting down to the kind of energies where you would expect, where you would be producing, LISA scale gravitational waves, then all of those things will be in scope for the kind of mechanisms that you might be thinking, if you're thinking about something that's kilohertz and above. And so it's completely, in some ways, if you went and looked for gravitational waves in that, in that higher frequency band, then you're really doing a blind search for new physics in the very early universe. And there's a vast range of potential production mechanisms.
Can I change a little bit the subject? Going back to your talk, you had your quantum sources and the classical sources.
Yes. I felt a little cheesy writing that down, but it's
That's fair. That's fair. Now, in the quantum sources, you mentioned that in inflation you may not get that much of a signal, but you say that model with contracting universe you can get something. Can you explain that?
Maybe I've broken the rule about never putting anything on a slide that you don't fully understand. But my understanding is that, roughly speaking, you're saying that I think very loosely, and this is probably more in your, it's more in your field of expertise than mine. I think you can say that the gravitational waves that are produced by inflation are essentially the de Sitter temperature of the horizon during inflation, and then they're very quickly moved outside of the horizon, so they're frozen in place until they return. And so in the case of inflation, we know that the energy density by design is almost constant through the inflationary phase, and so you produce this very weakly red background of primordial gravitational waves. So if BICEP 2 had actually seen gravitational waves, then you could go looking for them in the solar system, but they would be at somewhat lower amplitude than they would have been at CMB scales, but not by much. But in the case of these contracting models, they work because the co-moving horizon is shrinking as the as you rush towards this kind of almost big crunch. And so as they get to smaller and smaller scales, the value of H is getting larger and larger. And so the gravitational waves that they would produce in that scenario get smaller as the co-moving scales get smaller, which is, I think, kind of conceptually why things like the apyrotic scenario are associated with a blue, fairly steep blue spectrum of gravitational waves. So I think generically you would make the argument that those scenarios would be producing, there's obviously at some point that has to be cut off because there's a bounce. And so, where we are, where 1 gigahertz today is, relative to the Planck scale, near Planck scale horizon, is something that you would have to calculate. But I think generically speaking, the argument would go, generically speaking, the argument that these things don't produce a cosmological gravitational wave background is because the gravitational waves that they produce would be rising in amplitude. And so when you're looking at cosmological waves, you're looking at modes that would have had to leave the horizon when the energy density in the contracting phase is relatively small. I think that's I think if Paul or Neil was here, I don't think I've done too significant violence to their ideas with that summary.
Okay, thank you, Richard.
Okay, we have time maybe for one more short question or comment, if anybody has one.
If nobody has one, may I ask again, Richard, what kind of simulations are you doing? N-body or what?
So we're doing a variety of things. I mean, if you want to look at the preheating background, you have to solve the Klein-Gordon equation.
I'm talking about this long matter domination.
Right. So what we've got is we've got a mixture of N-body and Schrodinger-Poisson. And so the Schrodinger-Poisson equation is expensive to solve because you have to look at the very small scales in order to see what's going on, which means that your time scale grows quickly. And so what Jens and his people have developed is a code that is N-body on large scales because you can prove that the N-body dynamics and the Schrodinger-Poisson dynamics overlap on very large scales. And then in regions of particular interest where you would expect that there would be nonlinear dynamics going on, then in those regions you put in a Schrodinger-Poisson solver, and there's a complicated process for matching between the Schrodinger-Poisson solution and the N-body solution at the boundary. So they developed this for structure formation in the present day universe, and we've been able to apply it to the to the early universe. We'll have a paper coming out on this in maybe a week or so.
Yeah, in this way, can you see black hole formation, for instance? Because this was a Eugene problem, no? Eugene had a similar project, and they had to start from already from basically the non-linear stage to be able to perform the simulation. Otherwise, they wouldn't be able to start from
the answer is yes and no. So what we do see is we see the formation of solitons. So in the same way that these ultralight dark matter models say that like at the center of a halo there's this collapsed soliton, so it prevents at some point you can't compress this material because you're trying to make it smaller than its Compton wavelength, and this is what people in the literature call this quantum pressure that sort of provides a restoring force. So you can have something that has no kinetic energy but just kind of sits there rather than collapsing. And these boson stars that people talk about are the same solutions.
Yeah.
And so we absolutely see the formation of what we've called inflaton stars. So in other words, boson stars that are made out of inflaton matter. And we can predict, so we haven't run the simulations long enough to see gravitational collapse, but there's a fairly well-established set of scaling relationships that people have developed primarily in the late universe, but we've been able to replicate in the same scenario, because it is essentially the same physics. And so we can predict that there will be black hole formation if we wait long enough in these models, and in principle, how many black holes. As far as I can tell, I think there wouldn't be a lot of primordial black holes. It's not one of these scenarios where the universe becomes dominated by primordial black holes, but they're certainly there. And again, this is purely m squared phi squared inflation that we're looking at, circa 1983, that we can use. Having done this numerical calculation, then we can extrapolate it in various ways. Using, as I said, some fairly well-established treatments.
Sorry, Richard, so can you compute the probability of collapse to form black holes analytically?
So you can compute this. You can compute essentially the pressure sector. So you can compute essentially what's the halo mass function in the universe, and you can compare the numerical results to the
Yeah, but that gives you the mass. I'm talking about the density. I mean, can you be sure that you form horizons?
No, I mean, at the moment, no, we can't. No. So what you see is, I mean, we haven't. I mean, so to do that, you would need. I think as Francesco was sort of implying, you need to do that. You would need to use a fully relativistic simulation.
Yeah.
But there are simulations of the collapse of blobs of scalar field matter into black holes, and in general, the argument would go that the central soliton would start to get a mass that was close to its to its Schwarzschild. Well, it would. I mean, as the solitons become more massive, they become smaller because they've got a larger their self-gravitation becomes larger, and so the radius of a more massive soliton is smaller than a less massive one. And so at some point there's a crossing where they become close to their Schwarzschild radius. So the detailed numbers at which is it going to be twice like exactly when does it happen is something there would be uncertainty within a factor of a few, but I think we'll feel relatively comfortable saying that we've seen evidence for gravitational collapse that if it lasted long enough would produce things that were inside of their own Schwarzschild horizon. I think that will.
Okay.
That will be. I mean, we'll be careful about what we say. We're not going to say, "Oh, yes, we've seen. Here's a picture of the black hole that we found in our simulation," because that wouldn't be honest.
Yeah. So thanks a lot. I think we made fantastic use of the time zone overlap between Europe and New Zealand in this session. I think it's time to move on. But yeah, I mean, please feel